6-5. 6-5. I'm not going to call this 6-5A. We're just going to go 6-5 and do some. Okay, so we're going to do graphs now. Graphs of polar equations. And you'll get to use your calculator to graph these. So the book does show you how to do them by hand, but since we have these beautiful graphing calculators that we love so much, we're going to use them. Okay? All right, so in order to graph, we need to know some things about the graphs of polar equations, and we're going to start with talking about their symmetry. Okay, because as you know, you look over here, you go, whoa, there's a lot of symmetry going on. In my last class, they were talking about those projects, and they were like, does it have to be symmetric? No, it doesn't. Not all of them are if you look closely. But there's a lot of symmetry happening. So there are 3 types of symmetry for these polar graphs that we're going to talk about. 3 types. So type number 1 is when your graph is symmetric over the polar axis. Polar axis. Now remember, we are not an x and y axis anymore because we're in polar, which is r and theta. The polar axis is what you like to call the x-axis. So if something is symmetric over the polar axis, like say like your basic parabola, no, a sideways parabola would be symmetric over. Polar axis is the x-axis. All right, type number 2 is going to be over theta equals pi over 2. Think about the angle theta equals pi over 2. Think about the line that makes. What is that? Yes, it's the y-axis. Okay, so it's the y-axis is what you're used to. In polar, we call it theta equals pi over 2. And then finally, there's a 3rd type of symmetry. And this is the same symmetry that odd functions are symmetric. You know, odd functions are symmetric over the what? The origin. They don't call it the origin. They call it the pole. Yeah, the pole. Okay? And that's the origin. There you go. And your book talks about doing a test for these, and I taught it 1 year, and nobody really liked it at all. Like it's very complicated. When you test them, you have to test all this stuff. And okay, I know that you know that if you look at something, you can tell it's symmetric. You don't have to test it, okay? So if it tells you to test or prove, you can skip that part. Just tell me how it's symmetric, okay? So let's do some. Are you ready? Okay, number 1. Suppose that we have r equals 5 times the sine of 6 theta. Ooh, this one's going to be crazy. This one's fun. Okay, r equals 5 times the sine of 6 theta. Now, I want you to graph this on your calculator. We're going to sketch a graph, and we're going to describe its symmetry. Okay? In order to graph this correctly, you need to be in polar mode. And, ooh, you got it already. It's pretty, huh? You need to be in polar mode, and you need to be in radian. And then hit zoom 6 to make sure everything's all, you know, normaled out and stuff, okay? So polar mode, radian mode, and then you graph this. So I would go here, and I'd go 5 sine of 6, 5 sine of 6 theta, zoom 6. Ooh, that's so pretty. Isn't that fun? Did you like that at all? You can't? Do you have your calculator? Wow, this one's crazy. Yeah.
Are you going to tell us if we have to switch modes?
No. You'll have to know. So if you have to graph this, then you'll know that you need to be in polar mode. That's hard because you're switching between radians, you're switching between degrees, you're switching between parametric, polar, function. Yeah.
Polar is always going to be radian.
Yes.
Okay. And is parametric always going to be?
Parametric was radians too.
Okay.
Yeah.
And
And then directional angle sometimes in degrees with vectors. Yeah. It's everything all in one.
that's when we're just in function mode.
Mm-hmm. All right, so how are we supposed to sketch this, right? Are you wondering that?
Just draw a flower. There.
Yeah. Did you sketch it? Whoa, what is that? You can hit zoom square too. Zoom square helps a little bit. Not really, but it's so pretty. Isn't that fun? Okay, that's a pretty complicated one. I probably wouldn't make you really like sketch this too seriously. You know what I mean? Like just make like, looks like there's 3 petals in each quadrant. Are you laughing, Catherine, at my drawing? There you go. I'm no Van Gogh, that's for sure. So there you go. I'm more like a Picasso there. Definitely. But let's talk about its symmetry. That's hard to do on this. But the symmetry, what do you think it is?
Everything.
Everything, yes. And you don't have to test them all. That would be really bad. But this is symmetric over all 3. All 3. That's exciting, huh? Okay. Let's do another one, number 2. Here's one that you're going to love. That's funny. R equals 3 plus 3 cosine theta. We might need to change our window a little bit, but let's see what happens when we graph this one. 3 plus 3 cosine theta.
It's a heart.
It is a heart. Did you not get a heart?
What is the window? It's not yet a heart.
It doesn't, but it is. Okay, so here's the heart. Oh, you could ask someone to JSB with this. That's really cute. If you need ideas, just come to me. I have really good ideas. So you go to window. Let's change our window, okay? It's 0 to 2 pi. 0 to 2 pi. T step. Theta step is not T step, but theta step. Theta step is how many thetas there are in between. Like that's how many points they're doing. You don't need to worry about that. Let's do x min. Let's go -5 to 8, and y will go -5 to 8, I guess. All right, let's graph that. There you go. That's better. And you can see that's a heart. We're going to learn tomorrow that that's called a cardioid. Oh, I did -5 to 8 and -5 to 8. Okay, now let me teach you a couple other things, okay? So go back to your graph. So you should have this graph. Hopefully you have the same window as me. I did -5 to 8 for both x and y. And when you graph this, you need some specific points, okay? I don't want you to just like sketch a little heart and be like, okay, that's good enough. So we need to know what some of these points are. And here's an easy way to do this. You can hit trace. And the thing is, though, is that when you hit trace, it's going to give you x and y points. We don't really want x and y because we're on a polar graph. We want r and theta. So if you go up here to format, which is second zoom, and you look at that first one, it's giving you rectangular coordinates. If you go over here, you can go to polar. Hit enter on polar, okay? Now go back to your graph and hit trace, and it'll give you the first value when theta equals 0. So if theta is 0, that means 0 degrees or 0 radians. We're in radians. 0 radians gives me an r of 6, okay? So go out here to 1, 2, 3, 4, 5, 6, and plot that point. All right. Now, if I follow this and I hit trace, it's going to get me over around, and then it stops at nice places for me. So at theta equals 1.57, what do you think that is? What is 1.57? It's half of pi. At pi over 2, the y-axis, r equals 3. So I can go 1, 2, 3, and plot that point. Keep going along, and then you're going to get, ooh, at theta equals pi, 3.14, r equals 0. So the radius is 0, or r equals 0, so that's when it goes right to there at the origin, or the pole. And then if you keep going, it'll get you over there to 3 pi over 2 is 3 again. 1, 2, 3. And then you can probably, you know, graph it really nicely. I drew it in red. It's pretty good, huh? It's a little bit rounder than that. I don't really like that. It looks more like that. There we go. Like the peach emoji. Sorry. Okay, there it is. Cute. Really good. All right, so what's its symmetry, though? Yes, symmetry over the polar axis. Okay, you do not need to test for symmetry. You don't need to prove that it's, you look at it and you're like, there it is. I proved it. You know, it's not a proof, but that's where it's symmetric, over the polar axis. Okay, let's do one more and then we'll call it quits. And then tomorrow we're going to find out all their names. They have fancy names. They do. There's specific ones that have pretty cool names. All right, you try this one. R equals 4 sine of r theta. I want you to sketch a graph of this and tell me its symmetry. All right, so you try this one. This is what it looks like. It goes like this. It's like there's a petal. These are going to be called petals. It goes like that. And then there's one down here, and then there's another one there. Yeah, they're all the same distance, though. So it's a little bit hard to draw. Okay. Anyway, so what's the symmetry here? Symmetry over theta equals pi over 2. Okay. How far does it go out in each direction? Did anyone trace it around? 4. Yeah, and did you notice that it went to -4? Did you see that? When you hit trace and you go out to 4, that's at theta equals 0.5. I'm pretty sure that's at 45 degrees. Pretty sure. And then if you keep going and you go to here, that's at pi over 2, it's actually -4. Think about that. This right here is the point -4 pi over 2. Right? If I went to pi over 2, which is up here, but it's -4, I'm actually down there. Cool, huh? And then once you get back over to here, that's 4 again, that's 4 there too. Okay, so this is